Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part one of the lecture on regional skew. This is the 10th lecture in the course on statistical methods in hydrology. In this class, there are going to be three lectures that discuss regionalization. This is the first, regional skew, and then Greg Karlovitz has made videos on the index flood method and on precipitation frequency analysis. So we're going to hit regionalization kind of hard this week. Okay, so here's the list of topics we'll cover in this lecture. Note that the topics are broken down into four, and so we're going to have four lecture videos with one of these bullets in each video. Right, the first is why we regionalize skew, and we'll talk a bit about the sampling error in the skew estimates, and also a little bit about skew coefficient bias. Then we'll move on to the approach to regionalization, which has been known as trading space for time, or pooling information into a larger data set. Then we'll talk a bit about how skew is discussed in Bulletin 17B. The guidelines, Bulletin 17B did suggest doing regional skew studies ourselves, and I'll go through the various methods just so we have an idea of how it might be done. And then I'll also go through the derivation of the skew weighting formula between station skew and regional skew, which is used in Bulletin 17B and in Bulletin 17C. And then finally, I'll go through some of the updated methods for estimating regional skew, which has landed on Bayesian generalized least squares regression for 17C, but I'll talk about some of the in-between alternatives as well. Right, so starting with why regional skew as our first topic. Right, so why do we regionalize at all? There's three main reasons for regionalization when it comes to probability estimation. The first one is sometimes we don't have any data at all. If we don't have a gauge and we need to estimate something like a flood frequency curve, then regionalizing our information from the surrounding sites that do have gauges can give us information for the site of interest. Right. A second reason is that we can improve our probability estimates for a site for which we do have data by pooling data from many gauges to get the effect of a larger sample size. So here, let's think back to Monday in the introductory lecture. In the kind of work together demo, we all estimated the probability of rolling a 4 on a 6-sided die by rolling a die 12 times, or perhaps by updating a die rolling website 12 times. But either way, we each got the equivalent of 12 rolls of a 6-sided die to estimate the probability of rolling a 4. And except in some lucky coincidences, we all got pretty bad estimates of probability. But with 45 students in the class, if we had just pooled the 12 rolls from each person, we'd have had 540 rolls. And that would have given us a much better estimate of the probability of rolling a 4 than each person had with only 12 rolls, right? So that's the equivalent of what we're doing with regionalizing. Now with the dice, first of all, we already knew the probability of rolling a 4, but if we were trying to determine if our actual dice, which I would have given you in the classroom, were fair, then we would maybe have been interested in the probability. And also in that case, we're assuming that all of our rolls came from the same population, right? Regionalizing in that way, just literally pooling data, only works if we believe we have independent samples all from the same population, right? Most of our efforts at regionalizing are not exactly the same population, so we have to recognize that we're spread across different populations and build relationships between the data that we have and the characteristics that we have and a regionalized result. Okay, one more reason to regionalize is when we want consistent parameters of probability distributions in a region, right? If we're doing a study that involves frequency curves, maybe along a main stem, if we have different lengths of gauged record and some include some big events that happened in the past and some don't include those events, we can get very different frequency curves. And being able to regionalize will give us curves that are consistent with each other and make a study based on all of them a little bit more reasonable. So let's move on to what we should regionalize, right? There's various different parameters that we might use a regionalization approach for, right? First, we have precipitation frequency analysis for multiple quantiles and durations. I'm actually not going to say anything more about this in this video because we'll have a video from Greg Karlovitz on precipitation frequency analysis that we'll watch tomorrow. Okay, next we have quantiles of peak flow frequency curves. So USGS has developed equations, regression equations, for peak flow frequency quantiles like the 1% event that are based on watershed characteristics. And these are to be used in locations where we don't have data, where we don't have a gauge. So each will be a regression equation for, say, the 1% flow based on characteristics of the watershed. So by looking at maybe basin area and channel slope, we'll be able to predict the 1% value. These regression equations are built on knowing the flow quantiles and watershed characteristics for sites that do have gauges. We're going to be covering regression on Thursday and Friday, and so we'll see a little bit more detail about this. All right, and finally, the skew coefficient of the peak flow frequency curve. So this is what we're doing in this lecture. The skew coefficient is dimensionless, and so it's a little bit more convenient to regionalize across locations. And more importantly, it's really difficult to estimate accurately. I've said that in several of our videos for this week, and I'm going to show it even more so in this video. Skew is hard. Okay, so here's a reminder of what positive and negative skew look like, and what zero skew looks like. So a zero skew means a symmetrical probability distribution. Here it is as a PDF, and then here it is in our frequency curve form. This is a normal probability axis, and so a straight line means a normal distribution which has a skew of 0. A positive skew on the frequency curve is an upward curvature. So positive means happy and smiling, just as a way to remember it. And on the PDF form, that means we have a longer upper tail and the lower tail is tucked in. For a negative skew, we have a downward curvature on the frequency curve form, so negative, unhappy, frowning, and the PDF form has a long lower tail, and the upper tail is tucked in. So with a positive skew, we can have some very big flood events compared to the most of the distribution. With the negative skew, we might have had some very small flood events or just low flow events, but having the tucked in upper tail means it's not very likely or almost even possible to have large flood events. Okay, so here is a skew record. This comes from our Corps of Engineers guidance, maybe from 1415. This is like what we looked at in the uncertainty lecture. We're computing skew coefficient as an increasing sample size as we move across time. This goes from about 1910 to, I think, 1983. And the skew coefficient is recomputed with each year of data, right? So as you can see, the skew coefficient is quite volatile. It's all over the place back here in this first 10, 20 years, which is not surprising. But we have a fairly dramatic increase in the middle, going from about a 0.5 to a 1.9 with 1 year of data, right? And then continues, then starts to decrease and continues to decrease for the rest of the record in the same way that it was decreasing in this part of the record before that 1 point in the mid-50s. So what do you suppose the data set behind this running computation of skew looks like, right? Well, you probably guessed that there was a really big event here in 1955. And in fact, this was 2 hurricanes back to back, only a week apart, Hurricanes Connie and Diane, that caused this really large event in that watershed. Right, so this was what caused the jump in the computed sample skew coefficient, right? We suddenly have a really big tail on our data and got a very large computed sample skew. And I went ahead and continued this data set. That went until 1983, and so I downloaded the data through, this looks like about 2017 or 18, and the computed skew coefficient from the sample does continue to go down and ends up around a 1.0 at the time I made this figure. I'm still not that confident that we have an accurate skew coefficient for this watershed. It's probably going to keep on changing. This large event, the problem we're having here is this large event was probably not a 1 in 70 year event, right? It was probably a more rare event than that, back to back 2 hurricanes. So the skew coefficient is suffering from the outcome of that large event. And so we'd like to find better ways of getting a better estimate of skew, and that's where the skew regionalization is going to come in. Okay, so in the uncertainty lecture, we talked about estimators and sampling distributions of estimators. So the way we quantify our uncertainty in estimators is by looking at their sampling distributions. And the meaning of the sampling distribution is just the uncertainty in estimating anything, a parameter of a distribution or a quantile or a probability based on a limited sample. So in the uncertainty lecture, we worked with the estimator for sample mean, X bar. Right, and we built the theory of sampling distributions around that. Right, so if you recall, the central limit theorem told us that the sampling distribution for an estimate of the mean was asymptotically normal. So here's a normal distribution, and the sampling distribution was unbiased, is unbiased. So the mean of the sampling distribution is equal to the population mean mu. And it also has a variance that's proportional to sample size n, right? So the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of n. Right, so we're going to move on to looking at the same type of thing for skew instead of for sample mean. Right, so a reminder of what the picture looked like a little bit bigger. Here was our original population in blue, and our sampling distribution for the mean X bar with a sample size 10 was this pink curve, which had a center around the population mean mu, and standard deviation equal to population standard deviation over square root of n, which is square root of 10 in this case. And then for a larger sample, we saw in orange that our sampling distribution was a lot narrower, still centered on the population mean mu, but its standard deviation was equal to sigma over the square root of 50. Right? We went through a whole spreadsheet demo. We're not going to do that again. We're going to instead move on to looking at skew. But first, let's go through that review of the meaning of sampling distributions. We have across the top here parameters that we might be estimating, the mean, standard deviation, and skew. And then down on the left, we have the description of how well we can estimate those parameters, which is described by that sampling distribution, right? So the sampling distribution itself has a mean, which tells us whether or not the estimator is biased. It has a standard deviation or a standard error, which tells us how wide the sampling distribution is, which means how much error do I have in my estimates for a given sample size, and then how skewed the sampling distribution is. And in the uncertainty lecture, we went through this whole first column for estimates of the mean, and we also went through the standard deviation row to look at the average error in estimating each of the parameters. And in this lecture, we're going to go down the column for skew. Okay. So first of all, we're going to quantify how good an estimator is by the mean square error. Okay, mean square error is the average squared error in an estimate, at where the error is defined as the deviation from the true value. This is similar to variance, or the square root of variance, which is standard deviation. If you recall, standard deviation was the average distance from the mean, whereas the standard error is the average distance from the true value. But other than that difference, these are very similar estimators. Just a reminder, sigma squared is variance, sigma is standard deviation. The larger the mean square error, since it's quantifying how good our estimator is, the larger the mean square error, the smaller the confidence in the estimate, and the greater the error. Mean square error is proportional to 1 over n, and root mean square error is proportional to 1 over the square root of n. And in the previous lecture on uncertainty, we were talking about that as the standard deviation of the sampling distribution. Right, so mean square error of station skew is the thing that we're interested in right now. So we're going to go back to Monte Carlo simulation. We're going to do the same thing that we did in the uncertainty lecture. We're going to do numerical experiments to help us figure out how well we can estimate a given parameter with a given sample size by randomly sampling from a known distribution with a known parameter for a given sample size, and then re-estimating the parameter and looking at how well we can estimate it by comparing it to the true value, right? So for skew, we're going to do this for different sample sizes, and we're going to do this for different values of skew, because it turns out for different actual values of skew, the sampling distribution looks a little bit different. Right, so how do we do that Monte Carlo simulation? Well, we're going to randomly sample from a distribution with a known skew. We're going to estimate the skew from that random sample, and then we're going to compare that estimate to the true and known value, right? So that's just that Monte Carlo simulation that we've done. right? In this case, we're going to randomly generate 1,000 samples that each are size n equals 50. And we're going to sample them from a distribution with a known skew. And in this case, by the way, I'm showing skew as gamma, which is the Greek G. Right? So now for each of these 1,000 samples, each of a sample size 50, I need to compute the skew coefficient of that sample, right? So here's just the sample skew equation, and for each sample, I compute a sample skew from the 50 values. Here we have a histogram that's showing the 1,000 estimated skew values from my 1,000 samples, each of size 50. In this case, the actual skew that I started with was 0. Right? And when the actual skew is 0, the histogram I'm getting is symmetrical. And it turns out that the sampling distribution of skew is symmetrical when actual skew is equal to 0. That's not the case when actual skew is not equal to 0. Right? So another thing we need to get from that sampling experiment is not just the histogram of my values of skew, but I want to be able to compute that mean square error. I want that single metric. So I'm going to take the calculated skew from each of my samples and compare it to the actual skew, which on that first one was 0, right? So here is my error in skew squared divided by n to get the mean square error, right? We're going to repeat this experiment that we just did for many sample sizes n and for many known skews. Right? We're going to do that to determine mean square error of station skew as a function of the sample size and the skew coefficient gamma and the distribution that we're sampling from. And in this case, I did all these experiments with sampling from a log Pearson type 3. So this is the result of doing that kind of sampling experiment. I sampled from sizes of 20 up to 100. This one is sampled from a known skew of 0. And this really should be histograms, but it doesn't look very clear to have all of these histograms plotted together. So I just fit some distributions to my histograms, but they're kind of wonky because they actually are from data. So these are actually from my 1,000 samples of each sample size, having computed skew for each of them. So we see the pink is samples of size 20 with an actual skew of 0. They range from about minus 1.4 to positive 1.4. We can see that as the sample size gets larger, the distribution becomes narrower and narrower. So each sample has a more accurate skew estimate as the sample size gets larger, not surprisingly, although the distribution is still surprisingly wide even as skew gets up to 100, right? We're ranging from about minus 0.5 to 1.5 for an actual skew of 0. Right, so still pretty wide, but note all of these distributions are symmetrical, right? Because for an actual skew of 0, the sampling distribution is symmetrical. This is a table from Bulletin 17B, which is the mean square error of station skew as a function of the skew itself and the sample size. So we just looked at the very first row of this table for a skew of 0 and increasing sample size, right? And then down this column, we have increasing values of skew. It turns out that for a positive or a negative skew, we would get the same uncertainty. It's all about the absolute value of skew or how far it is from 0. So the table only shows positive skews, but the same applies for negative, right? So for Bulletin 17B, they did the same sampling experiments I just showed and found these mean square errors in this table as a function of skew and sample size. They also made life a little bit easier on us by estimating the mean square error of skew as a function of sample size n and computed skew coefficient g, right? So with this approximation, we don't really need to use the table. So let's look at some results from a paper called Just a Moment by Wallace, Matalis, and Slack that looked at the properties of the sample skew. And it looked at the sampling distribution of the skew coefficient as a function of actual skew and sample size, kind of like we've just been doing. But they summarized some really interesting results. So what we have here is a skew of 0, which would be the normal distribution, and then a Pearson type 3 distribution with increasing values of skew down the rows, and then increasing sample size across the top. And in the table, we have the mean of the sampling distribution of the coefficient of skewness. So this is going to show us whether or not our estimate is biased. Now, something that I will demonstrate if we have time in this lecture, but I'm not sure yet whether there'll be time in the videos. But if you look down in this last row, they noted that the equation for the sample skew actually has an upper bound based on the sample size. So if you have a sample of only 10, the highest value you can compute for skew coefficient is 3.16, right? If you have a sample size of 20, the highest sample skew you compute is 4.47. You can try this yourselves by coming up with a sample that you believe has the largest skew that you think you can produce and looking at what the computation is. So come up with a sample of size 20 that has the largest skew you think you can make and see what the computed value is. And if you've come up with the right sample, you will see that you get 4.47 as an upper bound, right? When we talk about this lecture, we'll talk about what that largest skew sample actually looks like. Right, so back to the table. These values are the mean of the sampling distribution of skew, and they found that for a skew of 0, the mean of the distribution was 0, meaning the estimator was unbiased, right? But as skew moved away from 0, the smaller samples have sampling distribution means that are less than the true value, meaning they're downwardly biased, although that gets improved with a larger sample size. Right. And the reason for this downward bias is this upper bound on skew. It's not that we just hit the upper bound at a large skew. We actually have a bias in the estimate all the way down to lower skews. Right. So the skew coefficient is downwardly biased, but that bias decreases with the sample size. Right, here's a look at the sampling experiment for a skew of 1 instead of a skew of 0, but the same sample sizes from 20 up to 100. So note the sample size of 20, again, has the widest distribution, and it actually is fairly close to symmetrical. And as sample size increases, the distribution gets narrower, but it gets more and more skewed, right? So even for sample size 100, we're a little bit narrower than it was at sample size 20, but we've got a very positive skew on the sampling distribution. It is still below the actual value of 1.0 for most of that distribution, showing us the downward bias. Right? So the other table from the paper is showing us the standard deviation of the sample skew. Right, so this is showing us the width of the sampling distribution of skew, again for skew coefficients from 0 up to 3, and for sample sizes increasing from 10 to 80. So this is similar to the root mean square error, but they're showing it as standard deviation instead. And what we see is, not surprisingly, the standard deviation is decreasing as the sample size goes up, meaning our estimate is improving as the sample size gets larger. But as skew gets higher and higher, the improvement across the increasing sample sizes gets less until at skew of 3, it's almost negligible. Right, so that's just a little bit of detail about the sampling distribution of the skew coefficient. It is not one that is really advantageous for estimating. Right, so just a reminder of what we just figured out. We're doing the skew column in our matrix. So this is looking at the sampling distribution of the skew coefficient. We found that the mean of that distribution is biased. It might be unbiased at a skew of 0, meaning we'll get the skew of 0 centered in the right place. But the mean of the sampling distribution of skew is going to be biased towards 0. Right, for all skews other than 0. Right, the standard deviation, we saw it as the table, but just a reminder that from the uncertainty lecture, we saw it as proportional to 1 over square root of n. And then the skew of the sampling distribution, we saw it for a skew of +1, and all those sampling distributions were positively skewed. If it was a negative skew that we started with, all the sampling distributions would have been negatively skewed. So that is the end of video 1, and we're now going to move on to talking about trading space for time.